Okay, well, welcome everybody. My name is John Vandelant, and I think I recognize a lot of names and know many of you. So welcome to our seminar. So I want to introduce Mark Leviton, Dr. Mark Leviton from NIST. Mark is the lead research engineer for the National Windstorm Impact Reduction Program at the National Institute of Standards and Technology. He has over 25 years in research on tornado, hurricane, and extreme wind effects on buildings and other structures. And with respect to tornado research, Dr. Leviton served as the lead investigator for NIST's National Construction Safety Team technical investigation of the 2011 Joplin tornado, as well as for the NIST study of the 2013 Moore tornado. Dr. Leviton also leads implementation of many recommendations resulting from these investigations, including chairing the SEI, that's for those of you that are not engineers, the Structural Engineering Institute of ASCE committee developing tornado load provisions for ASCE 722. The ICC committee that developed the 2020 edition of the ICC 500 storm shelter standard, and the ASCE SEI AMS committee developing a new standard on wind speed estimation in tornadoes. And so with that, welcome Mark, and I'll pass to you for the seminar.
Great, thanks John. Is my audio okay?
It's perfect.
All right, well thanks everybody. Appreciate John the invitation to make this presentation and share the exciting news about development of tornado hazard maps and load provisions for ASCE 722. First, I'd just like to acknowledge I could probably list 50 or 100 different co-authors and collaborators who made this all possible. Where you're going to see what you're going to see here today is the culmination of kind of half a decade worth of hard work on behalf of an awful lot of folks. I will apologize. I'll call out some names of some key contributors along the way as we go through, but there's so many, and I apologize if I skip some. But I'll just acknowledge initially my colleague Long Fan at NIST, and our contractors and collaborators with Applied Research Associates, Larry Twisdale and Peter Vickery, and a bunch of their team there. Are some colleagues with the center and also with the ASCE 7 committees, of course, Bruce Ellingwood and Terry McAllister, Jim Harris, and others, Frank Lombardo. Just a whole raft of an awful lot of people have contributed to this work. So I'm somewhat just the messenger here. Okay, so let's, and I know we John, when we first started talking about doing this, we were talking about kind of a structural engineering focus, and then we said for a smaller group, and then we kind of opened it up to a seminar, so it's a much broader audience. So rather than just spending all the time on the hardcore nuts and bolts of the engineering, I want to give some bigger picture context here. And the first one is, why don't we consider tornadoes in conventional engineering design right now? Why do we have to go through this exercise to create that? And I think there's a series of common misperceptions, and frankly, we've heard this for a lot of years since we've been doing tornado work, and even some of these have come even when we first introduced it at the beginning of the ASCE 7 cycle, that we wanted to try and develop tornado loads, even from colleagues on the wind load subcommittee. I think there's perception that tornadoes are too rare, and we're going to see. I'm going to put some of these perceptions up here, and then we're going to go throughout the presentation. I think we'll be able to answer all of those. And I think it will demonstrate that that's clearly not the case. There's perceptions, there's nothing we can do about them. I mean, they're just so devastating, they're so intense. I think there's a common misperception. We have inadequate knowledge. We've had this amazing amount of tornado research has occurred, particularly in the last decade, and particularly on the engineering side. There'd been a fair bit of work in meteorology and climatology over the years. A lot more big picture stuff, but not as much of what's actually happening on the ground where we need to know the tornado characteristics to be able to design buildings. Perception that maybe we'd all have to live in concrete bunkers, or we'd all have to live underground. The idea that if we're going to try and do something of this, it's going to be too expensive. And I think a lot of those perceptions may be shaped by the few violent tornadoes per year that make the headlines. And the idea is, if we're going to do anything about designing for tornadoes, that means we have to design everything for the worst EF5s that we see, a couple times a year. And that's clearly not true. And we don't do that for our other hazards. We don't design for the worst Category 5 hurricane occurring any place. We don't design for the worst earthquake that occur. We design based on target reliabilities and move through there. So let's answer some of these questions here. How rare are tornadoes? Well, there's over 1,200 tornadoes that are reported per year. And we know from a lot of work that we've done, there's a significant amount of tornadoes that are underreported. If we just look at a plot here from 1950, when we began keeping official records, and this is just the total number of counts, we see it looks like, wow, there's a big trend here. Is that climate change or something? No, I said, no. In the early years, we just didn't have a reporting system. And actually, this database was reconstructed for the early couple of decades from newspaper reports and other things. And so really only in the modern era, from about 95 on, we're pretty confident that we're capturing at least as many tornadoes as that we are. We've got cell phone networks, spotter networks, modern radar systems. But even then, when tornadoes occur in relatively unpopulated areas, a lot of them we know just don't get reported. And where do they occur in the United States? Basically east of the Rockies, right? We get some smaller numbers of tornadoes can occur in the western states, but they're typically not the larger ones. So this plot's on the F scale or EF scale from 0, which is the least intense, to 5, which is the most intense. Are really big tornadoes, which we only have maybe one or so per year. But we can see, and in the other states and territories, Alaska, Hawaii, et cetera, their tornadoes are very rare, and when they occur, they're very weak. So hurricanes and other things dominate the wind climate in those regions. And if we look more on a local scale, here in a plot from National Weather Service in Oklahoma City, just kind of showing over the 130 or 40 years or so, here's the plots of the tracks of the tornadoes, at least that were recorded. There may have been some, especially early in the years when population was less, that weren't recorded. And so again, we can kind of see that the tornadoes maybe aren't as rare as people perceive them. How many lives are lost in tornadoes? Well, back when we did some work that we did following the Joplin tornado and some analysis, we looked at the different hazards and the official statistics that tornado fatalities are greater than hurricane and earthquake fatalities combined on an average annual basis, with about 5,600 fatalities between 1950 and 2011. That number, as large as that is, of course, in the situation that we have today with COVID, it just changes your perception of all, but at least in terms of how people die in natural hazards and how that relates to our building and our built environment, that tornadoes are certainly a very large contributor to tornado fatalities, and tornado fatalities by and large occur inside buildings. So how big is this problem that we're talking about? So we design our buildings and infrastructure then for hurricanes, thunderstorms, flooding, earthquakes, snowstorms, but not for tornadoes. Well, the Insurance Information Institute published results from a study showing that over a 20-year period, recent period, that the events involving tornadoes, including wind and hail and other tornadic storms, make up basically 40% of catastrophic insured losses. Hurricanes and tropical storms come in second to tornadoes. They only account for 38%. So this is big, right? I mean, nobody questions that we need to design for hurricanes and tropical storms. How much damage is caused? Is most of the damage caused by the big tornadoes? Well, it turns out if we look at the plot here on the right, that looks at the losses per tornado and the total losses for all of the tornadoes. This is some work that Frank Lombardo did as part of our Joplin investigation of the Joplin report. And so if we look at the black line here, we see, and note this is in log scale in millions of dollars here. So we talk any individual EF0 tornado down here, which is a very low amount of loss, and those losses increase over several decades, right? Several orders of magnitude by the time we get up to the EF5. But when we aggregate across all of the EF0s and all the EF1s and all the EF2s, but of course, as I mentioned, we have something like one EF5 per year and a couple of EF4s per year. So we have so many fewer of those tornadoes that when we look at the aggregate amount of losses, except for the EF0 tornadoes, basically they're the same order of magnitude. If we could prevent all the losses from EF1 tornadoes, we could make a huge difference and a huge reduction in our amounts. If we could prevent all the losses from EF2 tornadoes, we don't have to only just be designing and saying, hey, we're going to be able to design everything for these highest losses here. And so basically, I say we don't have to design everything to withstand the most violent tornadoes if we're, and still, we can still be able to achieve some significant tornado damage reduction. If we look at the frequency of tornadoes of different intensity, that's over a 22-year period in the modern EF scale era, we see that about 60% or so or more are EF0, another close to 30% are EF1, 8% are EF2, and only a very small percentage are these higher numbers. So from these statistics, if we looked at combining those, we're going to EF0 and 1 together are almost 90%. EF0 through 2 are 97% of all tornadoes, or EF0 through 2. And if we look at the wind speeds over here on our EF scale on the top right, we see those are the kinds of wind speeds that we are close. And we'll go into the loads and the pressures that we get from 120 or 130 miles per hour are a lot higher than the pressures we're going to get from our current ASCE7 design for straight winds there. But these are sort of achievable without radical changes to our design and construction technologies and how we're building things right now. And also, in addition to the fact that these 97% of all tornadoes are sort of EF0 through EF2, if you look at even the bigger tornadoes, most of the area swept by the winds of those tornadoes is not actually the highest wind speeds. You only have a small kernel of EF5 wind speeds in an EF5 tornado. If you look at the spatial area, the work that Frank again did in our Joplin study found that about 72% of the total area swept was experienced EF0 through 2 winds, and 28% was EF3 through 5. So if we could get to the point where we're designing for something on the order that covers kind of our EF0 through EF2 tornadoes, basically that's going to cover 90% of all tornadoes, and even for the 3% of tornadoes that are larger than that, it's going to cover a large percentage of the area swept by those tornadoes. It's not going to cover necessarily the absolute worst, but we have things that we can do to read that. So what's the genesis for the work here that I'm showing today is our study for the NIST study of the technical investigation for the Joplin tornado. This was really the first study to include storm characteristics, building performance, emergency communication, human behavior. We looked at the assessment of each and those impact of those on fatalities, and we developed 16 recommendations for improving tornado hazard characterization, design and construction of buildings and shelters, and also in emergency communications. And so what I'm going to talk about today really is the culmination of 3 of our specific recommendations. One of our tornado hazard characterization recommendations was to develop a new generation of tornado hazard maps. And then within our design and construction recommendations, we had 2 recommendations, one on developing performance-based design standards for tornadoes, and the next developing design methodologies and design guidance. So let's talk about development of our tornado hazard maps. And this was our recommendation to develop tornado hazard maps for use in engineering design of buildings and infrastructure that would also consider spatially based estimates of the tornado hazard instead of the point-based estimates. And so we reviewed all of the existing hazard maps that were out there right now that at the time when we completed our report by 2014. We had a storm shelter, a map used for design of storm shelters, which is really a deterministic map. And then we had a couple of different maps from American Nuclear Society and the Nuclear Regulatory Commission. And all of those basically had some significant limitations. They did not consider the fact that the limitations on tornado reporting and missing tornadoes and things. There was no treatment of the target size. They're based on judgment-based wind speeds at a relatively narrow range of return periods, and uncertainties were not systematically considered. In addition to that, we had a significant opportunity to do more sophisticated work than was done in development of these maps, because ever since the EF scale tornado era, once the Weather Service adopted the enhanced Fujita scale, and then particularly with the development of what they call the damage assessment toolkit, where they started recording a lot of details about every individual, about a lot of the individual damage indicators that they use to record and rate tornadoes, that provided a very rich new data set for us to be able to use. So I could probably spend a half hour just on this one slide, but let's just give you a big picture overview. So this was basically ended up being a 6-year effort. We worked very closely with Applied Research Associates, Larry Twisdale, Peter Vickery, and the rest of their team there. A couple of years into the project, the Nuclear Regulatory Commission supplemented our NIST funding to include some analysis of the epistemic or the modeling uncertainties in here, because that's required for maps that are used in the nuclear industry, and they wanted to be able to use the end products that we generate here. And so just a kind of a 30-second overview. We had Major component here to study the tornado data and the climatology. So working with the NOAA and NOAA tornado databases, and particularly looking at the biases and the reporting issues. So we're able to understand what are we missing in tornadoes, and working out to develop regional climatologies that underlie the basis of the variation across the maps. We had to work on developing and improving the existing models for tornado wind fields. Particularly spend a lot of time looking at things like path length, intensity variation, right? You say, oh, it's an EF5, and it's not just some rectangle that has the wind speeds, right? That the track moves, that the storm varies in width and intensity over the time, over its path. So we looked at path width and radius to maximum winds, other things. We spent a lot of time looking at what the wind speeds are, right? The wind speeds right now are really based on a judgment. And so we developed an engineering model to determine what probabilistically then, what were the wind speeds given the tornado had an EF rating number or an F rating number. And then we, again, modeled some of these things that as we developed various models here, looked at the effect of the uncertainties, combined all of those to develop the hazard curves, and ultimately develop the tornado hazard maps. In terms of our risk regionalization, if we look at the variation of the tornadoes across the country, we see obviously we have different patterns, and there's a different climatology in different regions. If your eye just look at this picture on the top right, you say, hey, if we were going to develop two climatology regions, where would it be? It'd be sort of east of the Rockies and west of the Rockies, right? And that's what we have an animation here of a sequence of clustering. So if we look at we bin this up into different grid cells, and in each grid cells, we included some physiographic variables like standard latitude, longitude, elevation, standard deviation of elevation, like a roughness, how much is land or water, then tornado days per year, path length, occurrence rates for different intensities, point strike probabilities. And then we use a clustering technique to be able to break that up and to let it run and see where do we have regions that have some similar characteristics across all of these different variables. And we'll let this animation run a little bit. And basically what worked out with lots of different grid sizes, with different grid orientations and spacings and initiation points, with different combinations of these variables, we ended up in a lot of cases where we had basically about 6 different regions that hung together. And we ended up with a sort of hey, what's our traditional tornado alley that extends off into the southeast? Then we have a region across the Gulf and Atlantic coasts are dominated by hurricane spawn tornadoes. Then we have in the Northeast, and then we have some transition regions here. And then of course, then we have a region out West. And so ultimately through a lot of analysis, we ended up with the final 6 different climatology regions as shown here as primary regions, and then some sub-regions. A couple of those were subdivided. The big tornado alley area here, this region 4B, 4A, closer to the Great Lakes, had a little bit less intense tornadoes on average, even though they kind of hung together here. So it's pretty amazing. Even though we did lots of different variables here, that climatology hung together. We looked at tornado occurrence rates, and particularly this population bias, which is well reported in the technical literature. The fact that it seems like we have more tornadoes in areas that are populated. So if we look at this picture on the right as a way to visualize this, this is an image actually in Alabama. And the darker shaded colors have areas where there's greater number of building density, because damage to buildings, it's not so much population density, although population of buildings is somewhat pretty highly correlated. But in areas where we have a lot of population, in urban areas and a lot of buildings, it's a little bit different. But really the indicators are buildings, right? And trees and a few other things. But if there's a lot of damage to buildings, it's more likely that the tornado was going to get picked up. And so your eyeball can do a pretty good job here of picking out that, hey, it looks like we have more tornado tracks in the darker areas, right? And that's just because, if a tree falls in the forest and there's no one there to hear it, did it make a sound kind of a thing, right? If there's more people around, and even today in our modern age, if there's not something to damage, if there's not folks around, a lot of times the tornadoes just don't get picked up. And so we end up with the bias factors for these different regions that I showed you in the previous one. E=1 would be unbiased, which means we're reporting all the tornadoes. But in some cases, we're seeing 1.5. Hey, we're missing 50% of the tornadoes. Some regions have significantly different characteristics than others, and we used as a basis for our bias to determine what this bias was. Is let's look at the census tracts that have And we looked at the variation of number of tornadoes versus different census tracts. And once we get over the building density in census tracts, once you get over about 100 buildings per square mile, those curves pretty much flattened out. So for each of the different regions, we use the high density census tracts as in essence truths to come up with this bias factors to characterize our underreporting. This is a really busy chart. I'm just going to kind of give you the high level here because our wind speeds, we didn't just say, hey, oh, the NOAA tornado database said it was the EF2, so the wind speed would have been between 111 and 135. Where did that wind speed come from? That's a judgment-based wind speed that came from expert elicitation, where they develop lists of damage. We look at, hey, for each different damage indicator, a house, a school, some other kind of a building, or trees, let's look at the level of damage and let's guesstimate what we think the wind speeds were. Well, here what we did is we looked at all of the criteria that were used to evaluate these damages, but then went back and did engineering models. The houses were the single most important DI out of all of them. If a tornado was rated 3, 4, or 5, it's because there was house damage, and the ratings were typically based on houses. So we developed engineering models for 44 different configurations of houses, hip roofs, gable roofs, different shapes, different structural resistances, different nailing patterns, different sheathings, all of those different anchor bolts and cut nails, all these different characteristics. And then we kind of went through a process. We first for each one of these models using time stepping finite element models with running the tornado over the house in a probabilistic sense using Monte Carlo simulation, calculate the probability of damage for a particular house given a particular wind speed. Then we correlate that damage with the specific degrees of damage as listed in the EF scale. So we get the probability of getting a degree of damage based on a particular wind speed, use a Bayes approach to swap that around to determine what the probability of a wind speed was given an observed degree of damage. And then the correlation between what was the degree of damage and how did that become in the EF scale. Then we're able to use that to estimate the probability of tornado wind speed given that it was given an EF rating or an F rating. And so we can see here for each of the different EF0 through EF5 of the 6 different intensities, the blue dotted bars are these ranges right here from our EF scale, but we can see we have a much broader distribution, right? The mean values aren't too bad, especially for some of these, but we see a much broader distribution of these different wind speeds, and that factored into our analysis. So we took all of those different components as well as epistemic uncertainties. We developed wind speed exceedance frequency plots for each of the 9 different regions. So for example, here for region 4B, that's a kind of our hot center of the country. It's this upper curve right here. So 10 to the minus 3, we're up here at 1,000 years right here. And we went all the way down to 10 million years. And we have a hazard curves then for each of these different regions. One of the things is we developed these for different target sizes. So it turns out that for tornadoes, and this is one of the things that was in our, that we identified in our Joplin report, and Frank led a lot of work on that, is that the risk changes depending upon your target size. And so your wind speed risk, and if I would just say, hey, there was a tornado, I'll use Dallas, just that's where my family lives, whatever. And you know, if we live in a house, we said, hey, there was a tornado that hit near the Dallas airport. And if I just asked you, well, is it more likely that a house that hit near the airport, or is it more likely that the tornado hit the airport terminal building? And I think everybody would say, well, more likely it hit the terminal building. The terminal building's bigger. The same tornado is more likely it hit the terminal building, right? Well, if you put that into wind speed space, and what that turns out is you get a different, for the same return period, you get a different wind speed, a higher wind speed for a bigger target size. And that comes from what happens is if we have a geometric point target, say right here, if we have a tornado path in blue, and then what happens, you roll the dice differently, the same tornado occurs, but it occurs slightly different. If it offset, that tornado doesn't hit that same target. You have a bigger target. If we look here on the bottom right, then you roll the dice, a different tornado occurs, the offset tornado does hit that target. And so you see, or maybe it gets closer to the core of the tornado instead of the outskirts of the tornado. So the target size is an important effect here. And if we look at that in terms of the curves here, we have a couple of different plots. I'll just kind of point out the one here. If we look at the difference between looking at a building that's 4 million square feet, so a very, very large building, which is this curve, the very top curve, and a building which is basically a point target. Think of, say, something like a freestanding communications tower. It in essence has maybe a few square foot plan area. We have in this case, at a 3,000 year return period, we've got a 45 miles per hour difference in the speed. And of course, so the difference in these target size effects vary based on what region of the country and also based vary on what return period that you're looking at. So if we take all of this information, we use that to develop tornado maps, we get these hazard curves. We interpolate those hazard curves for whatever return period that we're interested in drawing the map. We input the details of those into a grid cell map. Again, we start out with our 9 regions and we have that. Then we put a Gaussian smoothing routine across that map to smooth out, because we don't know exactly where those boundaries are, right? What we did, one of the ways we treated epistemic uncertainty, as I told you, we did lots of different grid sizes and grid offsets. We did lots of different combinations of those different variables. And then we got a range of, and if we sort of bounded, hey, where did we get the boundaries for this region 4? This dotted line here that I'm showing is the inner boundary out of all those runs that we did with all those different combinations. The dark black line here is the outer boundary for that region. And so we averaged across those when we created those regions, but there's a couple of 100 miles typically across those. And we averaged across those, determined what those average uncertainties were in those boundary locations to develop the size of our Gaussian smoothing window, then pass this Gaussian smoothing window across the region map to smooth out. And so we don't have these discontinuities, which we know obviously doesn't occur. Then we went through ArcGIS with the kriging, and then we went through the peak smoothing and final hand adjustments to develop the contours. And so ultimately, what does that look like then? Is we have a series of maps. We produce maps for target sizes ranging from geometrical point all the way up to 4 million square feet. Those are all square targets. Target aspect ratio does have some effect. If you have very long and skinny targets, then the aspect ratio as well as the orientation become more important. For square or rectangles of 2 or 3 or 4 to 1 plan aspect ratio, the effect isn't so big. And then we produce maps at return periods ranging from 300 to 10 million years. And here are some examples. We have a 10,000 square foot in the first row right here. And I'm just happen to be showing you the 3,000 year and the 100,000 year. And we can see what these numbers are. Just because the number is a little bit smaller and hard to read, I've just put what the value is in the center of the country right here in the middle. And these are peak 3-second gusts at 10 meter height. So the results of this work is we basically developed tornado hazard maps that based on the first ever engineering derived tornado wind speeds produced for the U.S. They've developed through probabilistic models that are really best estimates rather than conservatively based. And that follows the intent of the ASCE 7 maps for hurricanes, led by Peter Vickery. And for straight winds, the work that Frank and I and Emil Simu and Peter and others collaborated on here underlie the maps in the ASCE 716. The maps incorporate epistemic model uncertainties, and the maps are applicable to the nuclear power industry, where both aleatory and epistemic certainties are required in the risk analysis. Put together a nice graphic here that just sort of gives the chronology of this work that we developed, published our Challenge Tornado report in 2014. As we started on the work, we had a big stakeholder workshop out at ASCE headquarters here with about 100 or so participants to get input on our plans to develop these maps. We worked with the ASCE. They had an ad hoc performance-based design committee before they stood up the new cycle. In 2017, they started the new cycle. We formed a tornado loads task committee to take all this R&D work that we were doing at NIST and turn that into standards. We had a second tornado maps workshop where we rolled out the tornado hazard maps and got additional comments for the broader community as well as the ASCE 7 community. We revised the maps again, incorporating that, and then we ultimately created our final maps as well as tornado load methodology, which I'll show here in a moment. And right now, and we'll talk about where we are, these last couple of yellow boxes and the status here later on at the end of the presentation. So it's not just maps, right? Wind speed, of course, V squared in our load calcs, V squared, wind speeds are the most important, but we have a whole raft of other parameters, and most of those have some differences in tornadoes. So we're working developing our tornado load methodology. We've based that on the ASCE 7 wind load framework. Worked closely with our mobile radar community to analyze radar measured tornado wind speeds, particularly some data from Center for Severe Weather Research and Josh Werman. And we collaborated with our other standards committee, the ASCE AMS standard on wind speed estimate, committee developing a new standard on wind speed estimation in tornadoes. Josh Werman provided us several dozen tornadoes, that some of which had not been recorded but never really analyzed before, and got vertical velocity profiles, where the cases where they had data very close to the ground. Frank took all that information and synthesized that to develop this plot that we see here in the upper right, that shows all the gray lines are profile plots from snapshots in time from individual tornadoes. The blue line in the middle is the was the median of all those, and then the red line on top of that is where we've put, and this is the square root of K sub z. So this is a velocity profile, but our pressure factor. But that's basically where we put what our design velocity profile was going to be. But we see here, while there's an awful lot of randomness and variation in here, we can see that near the ground, by and large, the wind speeds are more often than not, they're increasing near the ground, and we end up with something like this bullnose profile. And if we look down here in the bottom right, then we can see it's very different profile shape from what we have for our boundary layer profiles for exposure B and C. We also worked, and Peter Vickery led a lot of the work on this, to develop new directionality factors, new internal pressure coefficients that account for atmospheric pressure change, as well as a brand new factor to account for the effects of the vertical winds. In tornadoes, we have these if you're near the core, we have these significant vertical updrafts. And with our ultimate goal here then is we're trying to get tornado loads into the 2022 edition of ASCE 7. And so that's kind of the more R&D part. And now we're going to get into a little bit more of the practical application. So when talking to John, we wanted to get some of each of these. So I'm kind of switching hats now, taking off my NIST hat a little bit and putting on my ASCE 7 hat. So this is work that was led by our tornado task committee. So we had a group of about 30 or so hardworking individuals that met on a nearly weekly basis for well over a year, and a less frequent basis for a few years before that, to kind of go through, gather all this information, put it all together, and develop what will be an entire new chapter for ASCE 7, as well as all the hooks and handles and changes that we need to make in other chapters so we can have tornado loads in our ASCE 7 standard. So, okay, so we had to make, this is where we lay out the changes for what's happening. We have a few changes to chapter 1. We have to include tornadoes in our risk categorization table right here. We have a few changes. We have to make some changes in chapter 2 to the load combinations. Our first wind load chapter, we have to have a pointer that gets us to our tornado load. Then we have this brand new tornado load chapter. The complete set of provisions they're required for risk category 3 and 4 buildings. And this chapter heavily references our other wind load chapters. And then we have a new appendix that has tornado speed maps for longer return periods. One thing for those of you who don't work with ASCE 7 or the building codes on a regular basis, I'll point out, because we're going to come back to this a little bit later when we talk about risk categories. So risk category 3 are buildings that are structures, failure of which propose a substantial risk to human life. This is buildings like schools, assembly centers, theaters, other kind of buildings where you have a larger number of people gathered together often in a single room or in a single building. Risk category 4, buildings and other structures designated as essential facilities, buildings and structures required to maintain the functionality of other risk category 4 facilities. And so as it turns out, like I said, our requirements, and we'll go through the reasons why, but our requirements for tornado loads all apply to risk category 3 and 4 buildings. So they don't apply to houses, which would fall under risk, and most other buildings fall under risk category 2, houses and a lot of commercial structures and shops and things like that. And risk category 1, certainly not there. Those are agricultural facilities that people aren't in all the time, and storage and those sorts of things. So basically, it's just a few modest changes but important changes to chapter 1. In the definition of essential facilities, we've added tornado. Essential facility is building another structure intended to remain operational in the event of extreme environmental loading from, previously we had flood, wind. Well, now we've added tornado to the list of these hazards. When we go to load combinations, and I have to shout out here to Terry McAllister and Bruce Ellingwood. We worked with them a lot on developing and improving and finalizing these. So basically, and I'm just showing you the strength load combinations here, but we made similar changes to the ASD, where we've added In addition to wind load, we've added W sub T for tornado loads. Too bad T was already taken, that symbol. And basically what we've done, so for the two combinations, 4A and 5A, where wind load was the primary load, we've added, instead of wind, you also have to consider wind or tornadic wind. For combination 4, your gravity maximizes load in the gravity direction, and combination 5, which maximizes loads in the uplift direction. So just to understand that we had a lot of discussion about this separately. Tornado loads are treated as a completely separate load from wind loads. They're not a subset of wind loads. They're very different. I mean, we have, tsunami is a kind of a flood, right? But in ASCE 7, we don't put tsunami under the flood load chapter. They're significantly different enough that they're treated separately. They're handled separately with combinations and other things. So that's how we've done that. And just how this works then is when we look at, these are our table in the commentary. We've replaced with our principal load here. We just have W's replaced with W or W sub T. I think in the interest of time, I'll skip over a few of those details there. In chapter 26, we added to the first paragraph in our scope, we've added this new paragraph here that says risk category 3 and 4 buildings and other structures shall also be designed and constructed to resist tornado loads in accordance with chapter 32. And then we had it deleted. We had some material we had a specific tornado limitation that previously said tornadoes were not considered in the wind load, and we had some commentary about that. So we had to delete all of that material. And then we go to chapter 32. And our chapter 32, our brand new chapter on tornado loads, what we did, and for those of you who work with ASCE on a regular basis, we followed the organization of the sections so that we kept everything as parallel. We tried to keep it as parallel as we could because we're building off all of the regular wind load provisions. We have a few places where we had to introduce something new, but mostly we're modifying, occasionally deleting a factor that was already in there. And so what we did, even with our symbology, we used to have G was gust effect factor, now it's G sub T. So we have a subscript for tornado. A few times we had to use a TOR where we already had some some regular wind load things that had a subscript of T. So now I'm going to kind of walk you through just the highlights of how this methodology works and some of the key provisions. So this is on our first page right here. Our scope, this applies to buildings and structures that are risk category 3 and 4 that are located in tornado-prone region. So here's our tornado-prone region map, and that kind of, if you remember back, where do we have tornadoes? Well, basically east of the Rockies, right? And so we went through, we took the map that was our largest number of square footage for 3,000 for 3,000 years, and that was sort of our largest required map. And that's where that contour falls right here. So basically, if you're in the tornado-prone region in the dark shaded area, you at least have to do. Many buildings in that area would not be governed by tornadoes, but you're going to have to do a few more steps before you rule that out. The other important part about this is that it shall be designed to resist the greater of the tornado loads determined in accordance with the provisions of this chapter, or the wind loads determined with accordance with chapters 26 through 31. And we point out here using the load combinations provided in chapter 2. So you can't just, because there is some differences and there's some exceptions that are different and whatever with the tornado, you can't just look at and say, oh, okay, for this member, tornado load was a little bit bigger than that load. And so for wind, so I do that. No, you have to go in and kind of look at that as a whole through you look at your wind loads and then you look at your tornado loads and do those separately. We have a significant limitations, and this was really expanded in response to some ballot comments that we got, that we really need to make this clear, and this is an important thing for communicating to the public, that there was, some people are concerned that there was a perception, oh, we've added tornado loads. So that means if I design my building to ASCE 722, I'm covered and I'm safe from tornadoes. And so no, one, it only covers risk category 3 and 4. It doesn't cover the whole country. It doesn't cover the most intense tornadoes either. So we added some language here that shows tornadoes loads specified provide reasonable consistency with the reliability delivered by our existing main wind force loads in our wind load chapters. These loads are based on tornado speeds of 1,700 and 3,000 year return periods, and we'll talk a little bit more about that here in a moment. The tornado speed at any given geographic location will range from an approximately EF0 through EF2 intensity. That's dependent on the risk category and the effective plan area of the building, as well as the geographic location. So we're putting up on the first page of the standard, right up front here in the user note, not buried in the commentary. This is not covering you from the be all and end all in the worst tornadoes. Then we go through and say, hey, options for protection of life and property from more intense tornadoes include construction of a storm shelter and or design for longer tornado return periods. And that we provide you an appendix that has those longer tornado return periods. And so let's talk about where did we come up with that 1,700 and 3,000 years. So we formed a ad hoc reliability return period working group. That was a collaboration between NIST, ARA, the ASCE 7 load combination subcommittee and the wind load subcommittee. And particularly work led by, that was done with this was led by Bruce Ellingwood and Yu Lee, with a lot of input from Terry McAllister and Jim Harris. They adapted the reliability analysis that Bruce and Terry and others worked on for the ASCE 716 wind maps. And we adapted that for use here, and then conducted a series of risk-informed analysis that showed that those proposed tornadic load criteria provide a reasonable consistency with the existing criteria. And so our key finding was it turned out that the 1,700 and 3,000 year MRI for risk category 3 and 4 provided this reasonable consistency with what we have in our reliability requirements in chapter 1. And so if we look at that, then what happens is by the time we get down to the shorter return periods, that we don't really have any significant tornado risk. You're just not likely to get hit by the tornado at all. So you don't have any really tornado wind speed risk at these return periods for risk categories 1 and 2. And then for risk category 3 and 4, your regular wind return period in chapter 26 it turns out to be the same as our tornadic return period. I'll also just point out here, this is the beginning of the work here, and it's not to say that as we gain experience with this over time that some of these things may change when we go to the 2028 edition. Now, if you remember, I said early on that we don't necessarily have to do tornadoes everywhere. Just because you're in the tornado-prone region doesn't necessarily mean you have to end up calculating tornado loads. So the first thing you have to do is, are you risk category 3? This is our flow chart. Are you risk category 3 or 4? If not, then you don't have to design for tornadoes. Are you in the tornado-prone region? No, maybe you can bail out there. Then you can check, is the tornado speed greater than 60 miles per hour? The contours on our tornado maps go down to 50, and that's for interpolation if you have to interpolate based on different plan area sizes. But basically, if you're for your location, if your tornado speed based on your building size and location and risk category, if it's less than 60, then you're not going to have to design for that. And then lastly, if our tornado wind speed is greater, we have a test, because see, maybe you have a tornado wind speed that's greater than 60, but maybe you're in hurricane, maybe your tornado wind speed is only 60, but you're in Miami, and so your hurricane wind speed is 180 or 190 or something, and so the regular wind load may dominate. And so what we have for different locations, and also based on different exposure categories, because we only have one exposure for wind, we don't have different exposures. If your tornado speed is greater than half of your basic wind speed in exposure B, then you have to design, or if it's less than, you don't have to. So we have those different criteria. So we had a lot of feedback. Hey, I don't want to have to do all this work and calculate all these extra loads if they're not going to control. So we did the best as we could to give you a bunch of things you can check very easily to see. It still doesn't guarantee, even if you get down to this box that says design for tornadoes are required, now you're going to have to go through the process and calculate tornado loads. It may turn out that they don't control or that they don't control over wind loads anyway, but there's a pretty good likelihood that probably something will control. We also have a provision based on allowing performance-based design. And that's based on, we have a little bit of commentary, and that's kind of adapted and similar to the PBD provisions that were put into the wind chapters for ASCE 722. We talk about our differences in wind velocity, and those of you who work with this know what this equation is very well, our velocity pressure equation. And the differences when we go to design for tornadoes, we've removed the KD and we've pulled that out, and that's going to go into the pressure equations. And by the way, I think it's passed our main committee as well. Even the regular wind load chapters are pulling out the directionality factor as well, because directionality is more than a function of just the climatology. It's also a function of building geometry and things. So we have a KZ factor for tornadoes. The elevation factor doesn't change, and we have our wind speed, our tornado wind speed is different. And no topographic factor. I already showed you this. This is what our velocity profile looks like. So it's uniform up to the first couple hundred feet, and then it actually decreases a little bit. So what we can tell is taller buildings are not going to be controlled by, at least certain main wind force is not going to be controlled by tornado, because the increase in wind speed at height dominates here, but except for maybe at some of the lower floors and components and things like that. As we mentioned before about this, speeds are dependent on the plan size. So for risk category 4, we have this is an older version of that slide. This should be 16 maps. And we added one more size in here for 100,000 square feet. Sorry, didn't realize I didn't update that. And we call target size in the ASCE 7 standard, we refer to that as effective plan area. An effective plan area is, it's not so much if these are planned, if we look at this, if this is a diagram, this is a plan of a building, it's not so much this floor plan area, because the tornado isn't going to come here and go in and go out like that or something. It's going to see sort of, as what we said, is we're going to look at what we call draw a convex polygon around the plan area of the building. And that in essence is sort of the target shape or the target size that's of relevance. And we have some figures from the commentary. You can draw the convex polygon like this, or if you just want to simplify it, it makes a little difference. Just draw the smallest rectangle that you can where your building is inscribed inside there. And so that becomes in essence, our effective plan area or target size. Now, one of the things that we have for essential facilities that's a little bit different is, let's just say we have, if this building is a hospital and this building right here is our physical plant that is required to run the hospital. And if the essential facilities, which have to keep operational, remember I showed you that at the beginning in our definition. Well, if this building, the small building, is required to keep this building running, then when you figure out what your effective plan area is, you have to encompass all of the buildings that are facilities that are required to keep the building. Maybe you have some fuel tanks here, which are fuel tanks for your backup generators. Even though it's not a building, then those fuel tanks have to be in, or maybe those fuel tanks are out here, then you're gonna have to draw a larger polygon. So I showed you a few of these maps. Here's what a couple more of these look like, particularly for risk category 3 and risk category 4. Again, we have 8 different sizes. I've just showed you here, 10,000 square foot is kind of a smaller building. We go up to 1 million square foot is a bigger building. We also have an appendix, which gives us return periods for 10,000 up through 10 million years. Our pressure equations, this is what our pressure equations for main wind force and components and cladding in ASCE 7. Those change. Some of the terms change. We have some new terms here in our tornado world. Our Q's are different, right? Because we just talked about, hey, our velocity pressure, I showed you that equation is different. Our gust effect factor is a little bit different. We have our directionality factor is different. We've added this new factor to account for the vertical winds. And then our internal pressure is different. So pretty much everything is different except for the basic coefficients, pressure coefficients that we start, the shape factors. For the gust effect factor, basically we're just saying use the rigid structure provisions. We have limited knowledge of that effect, but certainly the flexible structure isn't relevant. For tornado directionality factor, we adapted, and Peter led the work on that to adapt a method that was used to develop the directionality factors for the straight line winds. And then we have this new modifier, which basically affects the uplift on the roof when you have these updrafts. If you're near the core of the tornado, you have the significant updrafts, which enhances the uplift on the roof. And so a few of these factors, what they look like, are directionality factor. Not too dissimilar from the numbers that we use regularly. We have for main wind force is 0.8. Let me do the bottom two here. Based on in roof zone 1 prime, so that's the middle of really big roofs. We have a little bit higher uplift. For other cases, it's a little bit lower, 0.75. But note here for essential facilities and for buildings required to maintain for components and cladding, essential facilities and building other structures required to maintain the functionality, we've got this as 1. I mean, the directionality factor accounts for the reduced probability that the worst wind speed comes from the worst direction for the building from an aerodynamic standpoint. And so that's probabilistic basis, but for components and cladding, if it's an essential facility, we don't want to have any piece of the cladding ripped off, not just limit it to just a few pieces of cladding coming off. And so we don't want to have that. By the way, there's a parallel change under the regular wind load provisions to this one as well for essential facilities. So it's going to be hospitals and emergency operations centers and things like that we're going to require a KD of 1.0. Our vertical adjustment factor, we can see basically for the roofs of buildings, for main wind force, it's 1.1. For the roofs, depending upon what your roof slope is and which roof zone you're in, we can go from about 1.05 to 1.3. For all other surfaces, this becomes 1. So what this does, this KVT is a multiplier on our pressure coefficients. Our internal pressure changes a little bit because some work that Peter led and through some analysis was done and validated against some work that Long led on our Joplin tornado study, looking at the performance in the Home Depot and Joplin and the Walmart buildings. is that the atmospheric pressure change turned out to be more important than we had previously understood. And so for enclosed buildings, for enclosed buildings, we have a change where we have, instead of plus or minus 0.55, if the building is pretty well enclosed and fairly tightly sealed, that's going to be a worse case for internal pressure due to atmospheric pressure change. So we get a plus 0.55 here. And then we have a sealed other structures like tanks and vessels and things like that. So otherwise, the rest of these are the same. And lastly, let me end up with just a couple slides on a case study. And this some work that was started by Ben Harris and Blake Haney with a firm called Huckabee, and collaborating with them and got their permission. They this firm Huckabee designs education designs buildings for the education market in the Dallas-Fort Worth area. And so they said, let's look at some typical buildings. And then I asked them, could they also, while they're looking at this, in addition to looking at schools, can we look at fire stations, hospital, elementary schools? So they looked at some sort of typical prototype building for an elementary school, a high school, a fire station, a hospital campus. And they had some assumed geometry for each one of these different that was typical for what those are. And they looked at just some of the basic criteria. They looked at different exposures. And I'll just show you an example of what this means in load space right here. So in terms of the load changes, and it's a busy plot. I'll just take a moment here to explain. So green bars are elementary school. Red bars are the brown bars are fire station. Sorry, green are elementary school. Brown is high school. Red is fire station. Blue is hospital. And then the solid bars are wind loads in ASCE 716, and the crosshatch bars are the tornado loads. These are in the Dallas location, so those are based on Dallas wind speeds for these kind of facilities from ASCE 716, and Dallas wind speeds from the tornado maps for the same building sizes. And we can see that the pressures on the windward wall, pressures on the leeward wall, the net lateral force, the uplift on the edge of the roof, the uplift in the field of the roof, we can see the tornadoes go up quite a bit, right? Now, I will add a caveat that Dallas is one of the worst areas. There's kind of this region from sort of Dallas through, kind of North Texas over through southern Arkansas and extending a little beyond, where we have something of a valley. We have a trough in our regular ASCE 716 wind speeds. They're relatively lowest, but we're also at the southern edge of the highest tornado wind speed. So that area, that kind of geographic location, kind of North Texas, southern Arkansas, wherever, is the area that has some of the worst, where any of this comparison is going to be worst in the country compared to what tornado loads would be compared to your regular ASCE 7 wind loads. So this looks pretty dire. Wow, this is going to have a big impact. Well, they also did a cost study, and they looked at, there's some limitations. They didn't look at glazing costs and roof shingles and stuff, but they were looking at steel and structural framing and all those sorts of things. And basically what they did for a couple of different exposures, they came out with that the actual cost increases were not going to be very much. And if we look at it as a relative percentage increase of the overall project to build a new school or build a new hospital, actually they only did schools here, build a new elementary school or build a high school, was only on the quarter of a fraction of a percent. And so now, again, there's some other limitations here. We're actually be working with our NIST Applied Economics Office to do a more detailed study on cost effectiveness right here. But it doesn't look like it's going to break the bank to make these changes. So where are we at? Just wrapping up here, the current status, all of these tornado ballot proposals for all these changes. The ballots themselves had received passing votes from the ASCE 7 main committee, but there was some comments, and so we're working through resolution of those comments. By the way, ASCE 7, all committee meetings are always open to the public. You can find the meeting schedule on ASCE website. And this will be wrapped up in the next 6 months or 5 months or so. There'll be a public comment draft posted in June to July timeframe for 45 days. All comments must be considered by and responded to by the main committee. So hopefully, though, as we're working through this at this point, we don't see any major roadblocks to adoption of these provisions as I've laid them out to you. And we have a series of publications coming soon, a major report, which is in review right now on the development of these tornado hazard maps. We have another report, development of the new K factors. And then lastly, a report, we're collaborating with, again, Bruce and Terry and others on the development of the probabilistic approach for understanding the reliability and the return period analysis. And so over the next several months, all of these publications will be making their way through the system and become available. So with that, sorry, it looks like I'm a few minutes over, but open it up for questions.
All right, thank you, Mark. That's a lot of material in 50 minutes. So So with that, in the interest of time, what I'll do is I will read some of the questions, and then if one is real complex, so we'll run a little bit over. But again, this is being recorded for those of you that do have to leave for a meeting. So so the first one, and I think you just answered that, but are the from Christopher Allen, are the tornado hazard maps publicly available?
No, not yet, but I said in the next few months that report will be published and then they'll be available.
Okay. The next is from Alex, and it's mobile Doppler observations suggest that tornadoes can be underrated compared to damage surveys. In addition, tornadoes that are not surveyed or don't hit any damage indicators can receive a rating of EF0 even if they were much stronger. Is this accounted for in the development of the return period wind speeds?
Yes, we did. I only just, again, we did in our limited time, I only talked about the bias, accounting for biases of whether or not a tornado was reported, but we also did a lot of work to look at the bias on the reporting level, and very clearly the fact that many tornadoes, particularly in areas where there's less building density, they end up getting underreported. Even if the tornado was listed, if there was no building to hit or strong building, if it could only hit a mobile home or a barn, which can't sustain very high wind speeds, you can't get a high recorded wind speed out of that. Probably the most famous case about that was in the El Reno tornado in 2013. There was mobile Dopplers there, and they measured wind speeds close to 300 miles near the ground. And so based on the damage survey, the Weather Service rated the tornado as a EF3 because that's the most damage that they could find where it hit and the buildings it hit. And then they updated it to an EF5 based on when they analyzed the radar data, and the Weather Service made them change it back to a 3 because, hey, the EF scale is a damage scale. We can't be mixing and matching, even though it's got its own limitations. We need to stick with that. So anyway, we're trying to work on that with this wind speed estimation standard and improving the EF scale and improving other methods. And there's progress coming on that front that will improve reporting of tornado wind speeds and appropriate intensities that'll be coming down the pike in a few years when that's published.
Okay, thanks, Mark. Yeah, definitely a challenge. And then the other, and I think you've answered this also, but is the understanding correct that there'll be no recommendations for residential buildings?
Not in ASCE 722. Now, of course, anybody could do optional design. There won't be a requirement for it, right? You could use these provisions and maps and to design whatever level that you wanted to and calculate those loads. In our implementation plan for our Joplin Tornado Research is further down the line, we will be taking, once this is accepted, whatever, we will be taking and looking at what are cost-effective things that we potentially should be doing. Perhaps I'm pretty convinced that, and hopefully further analysis will bear this out, that adding hurricane clips to hold your roof down is probably going to be a very cost-effective measure even across the Midwest, to say. So I think we're going to have a separate track where we look at what things are going to be cost effective in terms of reducing tornado damage, and work to develop a design guide for that, and see if we can get some of those things into the building code, into the residential code.
All right. And then from, let's see, we have a question from Ahmed. How is the pressure deficit towards the core of the tornado considered in the tornado loads?
Well, of course, the pressure deficit is what drives the wind field. We looked at would there be a way to account for the fact that if the pressure is less, then our density is less, and would that actually decrease? Our 1/2 rho v squared, is the rho going to be less, and would that have an effect? There wasn't really enough work that was done on that. It potentially could have been modeled. We didn't include that, which, by the way, we don't include that for hurricanes either, and that's actually something that we're working with Peter Vickery and Applied Research Associates on our Hurricane Maria technical investigation. We are doing some wind field modeling, and we will actually be looking at that factor, the fact that, of course, it's a low pressure, so we have lower density, and does that factor, could that, or should that need to be factored into our load equations? It'd be a fairly minor adjustment, but it could be a factor.
All right, and then from Sohib, building.
I'm sorry. Actually, I'm sorry, John. The one other thing which maybe I think I was answering only probably the wrong part of the question, and I wonder if he meant, I talked about atmospheric pressure change, but perhaps that's what the questioner meant. The low pressure from the standpoint of the loading on the building directly, if the building is pretty well sealed, when you have that low pressure goes over that, then that creates, in essence, a positive internal pressure inside the building and that atmospheric pressure change. And that was accounted for when I showed the table of the fact that we have to use, even for a sealed building, we want to use a plus 0.55 as our internal pressure coefficient. That is accounting for when the lower pressure moves over the building by itself. So that's accounted for that way.
Okay. Okay. Thanks, Mark. And Ahmed, if that was not answering your question, you feel free to retype it or unmute and ask.
Oh, I think, yeah, it answers my question. Thank you so much.
Okay, great. Our next question is buildings close to the core center, max suction pressure, or at the core radius, max swirl related wind speed, face different types of wind flow structure interaction. Could you please let us know how to design for such cases?
Yeah, we don't have any sort of differentiation for that at the moment. The only thing that I'll say is in the development of this factor for the KVT, and actually to some extent in development even of the KD factor as well, we accounted for the fact that, of course, you know, our standard is kind of a one size fits all. We don't know exactly where the tornado is going to hit. Some buildings, actually about 80%, works out about at wind speeds, and this is a function of where you are in the country. It's a function of building size. It's a function of tornado intensity. But once you get up to a little bit over 100 miles per hour, then I think about, if I remember, about over 80% of the buildings, based on the modeling, would actually have some part of the building that would experience at least some winds near the maximum. And so some part of the building would be in the core. There are some buildings that are still going to experience significant winds that are a little bit farther afield. And so when we developed the things like the KVT factor, we don't know. We could have had a KVT factor for inside the core. And then if you're outside the core, based on some farther difference away, then you don't have a KVT, and then you have to transition between those. But we don't know where that's going to occur. So what we did is we averaged out, we accounted for the fact that only 80% of the buildings or so are in the core, and some smaller percentage are outside the core. And so we averaged out and actually reduced the KVT a little bit just to get, you know, what would be appropriate sort of for all buildings across. So that we're not always, and that was like our approach that we typically took in most other cases. We're not trying to get the worst of everything and pile the worst of the worst of the worst of the worst. You know, in most cases here, then the way this was done was that these were sort of our best estimates. And then, of course, in the reliability analysis, when they weren't, then the distributions of these different ones were taken into account. And when we picked a nominal value that was different from the mean value, et cetera, then that and any additional safety margin, whatever, gets factored into those reliability calcs.
Okay, thank you. This question is, this is a tricky one. It's basically from Bill. He got into the meeting late, but has the committee discussed how to handle issues with airborne missiles? And it's not really a wind force issue, but a detailing issue where they may be generated. Was there any discussion on that?
Yes, we have, and I just didn't have time in the presentation today. We have some provisions that relate to windborne debris and windborne debris protection for essential facilities, which we saw are required to remain operational. There, you're going to require to have windborne debris protection, which is this, and we picked the level which is the same as the hurricane level protection. So there's a lot of products and things that are out there on the market right now. And of course, like I said, we can certainly we can have much more intense debris, but again, our tornado speeds are lower. Where at least our required tornado speeds are not the 200 plus miles per hour that we see in the EF 4 or 5. These are the EF 0 through 2, and so that's going to provide us with protection. The other thing that we did is, because we have, even for the same wind speed in a tornado and a non-tornado event, because of the updrafts, we do see a lot more debris, relative amount of debris in the tornadoes compared to other wind events, and so. For all of our facilities, if you don't have impact resistant glazing or some other mechanism to protect from debris, then basically you're going to have to assume that some of those windows are broken when you go to calculate your enclosure classification. So that's going to potentially impact your enclosure, and you may end up with if you don't have protected glazing, you'll end up have to design for partially enclosed, so you'll pay somewhat of a penalty. So there is some provisions for debris. Now, those provisions will not be effective when we look at if you're using the long return period appendix, and that'll be something we'll need to develop for 2028. is some better missile criteria for if you're really looking at the longer return periods. We have much higher tornado speeds.
Okay, and we get one more question. What limitations in the knowledge about tornadoes prevented the development of tornado-specific structural analysis provisions before?
Well, let's see. I kind of went through just a few snippets of these different things. You could have done it, and we have. And let's, if we back up for a second, we've been designing for tornadoes for a long time. Nuclear facilities are designed for tornadoes. We design storm shelters. FEMA has criteria for safe rooms. We have an ICC 500 standard that's been around since 2008. Many thousands of safe rooms and storm shelters have been built. Many of them have been hit. There's not been a single reported failure or injury or fatality in any building that's been documented to have been built to those criteria, and a lot of them have been hit now. And so we can design, and we've made some more other simplifying assumptions, and even the ICC 500 standard, which a new edition of which just got published last month, that's got a bunch more. It didn't have all of this additional R&D behind it. We made some assumptions. We had made the assumption that KD was going to be equal to 1 for that as in essence like an essential facility, being as a shelter. We had done some other things. We had a deterministic map. I think I showed that on an earlier slide. So we are able to design for tornadoes. We haven't been able to design it as effectively, as efficiently, because we didn't have all of this more sophisticated details that we've been showing today.
Okay, well, with that, I think that is all the questions. So first, before we close, I just want to let people know that there'll be a link to the recording posted on the Center for Risk-Based Community Resilience Planning's website here at Colorado State, and you can email me or our general email address if you need information on that. And then I just want to, Mark, want to thank you for just an exciting seminar and really state of the art in research and state of the art in practice to come here in 2022. So thank you for preparing that and for your time on behalf of everybody.
Well, thanks so much, John. Thanks for the opportunity to present and get the word out. And I'll just close by just also thanking all of my many collaborators and colleagues who've worked together to make this a possibility, including those I mentioned, and a lot of those I didn't.
All right. Thank you, everybody. Have a great afternoon and stay safe, and talk to you soon. Thank you, Mark.